So this talk is called Movement Matters, Using Swine Shipment Patterns to Identify Farms for Targeted Disease Surveillance and Control. And I apologize, I just only found out I was giving this talk late yesterday, so I may not be extremely familiar with the layout of the slides, so I apologize in advance. So the purpose of this talk and this project was to describe swine movement patterns in production systems in two regions of the United States. Of course, the United States is unlike many other parts of the world. We do not have good government-level traceability programs, so we have actually very few descriptions of what swine movement networks look like available in the published literature, and that's a huge contrast from most of our European trading partners as well as in South America. So first, we're going to describe the patterns, and then second, describe and discuss results of this analysis and how we can actually use movement data to better understand how disease may spread and how we may be able to do better targeted control of pathogen spread. I have to figure out what these slides say, sorry. So we know that infectious disease epidemics are important to livestock and that there's numerous diseases that can have and do continue to devastate the industry. This includes both endemic pathogens like PRRS and PED, but also foreign animal diseases, which we don't have much experience with here in the United States. But if we understand how viruses move around and how pigs are moving around, we might have a better idea of then, if we did get a foreign animal disease, how it might move and how fast it might move through our systems. And we know that a key determinant of how diseases are able to move from farm to farm is contact. And of course, the contact that we're going to be primarily talking about is the movement of pigs. Of course, if you're moving infectious pigs around, then you are moving disease around. And we're going to be talking a little bit less about other forms of contact like feed trucks or feed ingredients or other ways that pathogens can move. So we can describe contact in multiple different ways. A lot of models will be over here and assume that, we just assume that all farms are in contact with all other farms, which seems a little bit unrealistic, but believe it or not, people do run models and simulations based on that assumption. Other ways we might be able to quantify the types of contact is through just some sort of local interaction model, which would be here in the middle, where you just define, okay, we have farms are connected to farms nearby, and that's who they can potentially transmit to. So both these middle ones are just like different ways that we could account for local contact. But of course, when we move pigs, this is a very spatially independent process. I mean, yes, most movements are occurring at slightly shorter distances, and there's of course a geographic component of that. But just looking at distance between farms does not give us a good proxy of should those farms be connected via movement. So we use a network framework to actually connect farms in that situation. So network analysis is a method to look at relationships through mathematical graphs. It sounds complex, but essentially a network is we have some set of nodes. So that's all these circles here. These are farms. Well, they can be really anything, but for this talk, these are farms. And then the links between them, so these arrows represent the contacts between them, so that each arrow would represent a discrete shipment of animals that have been moved from one farm to another. So we can use this to build up the network of contacts amongst, a group of farms. We have been looking at these networks in 3 different production systems in the United States. So these are all fairly large systems. And this just gives you an idea of what this looks like. They all look somewhat similar. They're all very highly connected system. Each of these systems we had about 1 year of data for, not necessarily the same year. And the data is a little bit older for this talk now. This is mostly data from 2013 and 2014. So there's a few things once we have a network that we can do with the network data. Why would we actually want to build a network? Well, network analysis actually gives us a tool to actually be able to measure contacts and quantify patterns of connections within these systems. So I'll go through a little bit of jargon. We won't go too deeply into what these are, but just enough so we all can talk about the same things. One of the most basic things we would measure in a network is the degree. So we would measure the degree of each farm, which is just a fancy way of saying that we're measuring how many connections each farm has. So farm A here has a degree of 1 because it has one other contact. Farm B has 2 contacts. So pretty straightforward. When we have networks that we call directed networks, where each contact actually has a direction, right? So all contact between farms has a direction because the truck is moving pigs from farm A to farm B. So we can also look at the in degree, so that's the number of incoming contacts a farm has, and we can look at out degree, the number of outgoing contacts that the farm has. So these are our 3 systems again. Now we have represented this where we've calculated in degree and the out degree for each farm by production type in each of these systems. And each dot on this graph represents a single farm. So this green one here is a nursery farm. And the x-axis down here is its out degree. So it's an out degree of around 8 farms. So it's connected to 8 other farms. Those are probably finishers. This does not include movements to slaughter, by the way. And the y-axis is in degree. So if we look at this farm here, it has 8 outgoing contacts and it has, looks like around 6 incoming contacts. So that nursery is receiving pigs from at least 6 or from 6 other farms during this 1 year. So first thing you can see here, these are all kind of obvious patterns. That's where we're kind of starting here. That the blue farms, these are our finishing farms. They have very low out degree because we're not considering movements from finishing to slaughter, and they all have high in degree. And then we see generally that these sow farms, these yellow ones, tend to have higher out degree and lower in degree, and the nursery ones tend to have relatively high in degree and out degree. That's what we'd expect in multi-site production. The other thing is that is important to consider is that these contacts don't exist all the time. We could consider it just a static network, and if farm A and farm B has ever moved pigs together, we just always consider that potential contact to be there. But that's just not very realistic. We know that these things change through time. A shipment occurs on one specific day, and it may be repeated through time, but it doesn't occur all the time. So that's what this top figure is pretty much showing is how these things or these connections change through time. And then we can start thinking about indirect connections in the network. So for example, if we take this farm here, we have a network of all of its incoming contacts. So this is not just the farms that it directly received pigs from, but the source farms, where did they get pigs from? So we're starting to move backwards in the chain because all of the, whatever infection's going on and all the way down far into this incoming chain, all of this could eventually end up in this farm. So we'll start looking at both the incoming infection chains and the potential outgoing infection chains, which basically is just looking the other way. So we have this farm here, and this is all the places that if this farm was infected, we would expect a pathogen to be able to get maybe to all of these farms, potentially. So that's the outgoing infection chain. And then we can also take into account the order in which those connections are occurring, in that, if this connection here, for example, can you guys see this pointer? It's very faint to me. Okay. So if this connection here occurs before this connection here, obviously then there's no actual path through this network from this farm to that farm. So we've also taken into account the temporal or the temporality of these movements, and this is what we call a dynamic network. So we have taken the incoming and the outgoing infection chain and basically use that to define the mean infection potential of a farm. So for every farm, we can measure how big is their incoming chain, how big is their outgoing chain, and use that as a metric as how important is that farm for potential spread in the network. So we did this for every farm and summarized it by our production types and by production system. And we did find pretty consistent differences that certain types of farms of given type have a characteristic way that they move, but it's not consistent across all these systems. So here in system B, for example, the types of farms with the highest mean infection potential are actually the sow farms. and then followed by the finishers. But then in production C, the finishers actually don't seem to be as important as in terms of their mean infection potential. We also want to quantify the overall vulnerability of the network to disease spread. And we do this through a metric called R naught, which is something that comes from epidemiology. R naught is simply a metric of the number of secondary infections that are expected if a single infected individual, and here an infected farm, is introduced to the population, assuming that the population is naive. So here we have a population of farms. So when we talk about R naught, we're really saying if one farm becomes infected, how many other farms are going to become infected from that initial case. So this is just essentially a measure of the potential contagiousness or the transmissibility of the disease. And we know that the network is important for determining these sorts of things. And of course, you could say, well, you can't really do this without understanding the pathogen, because that's really important. How long is the infectious period, and et cetera. But we do know that it should be proportional to contact rate. So if this is R naught, inherently we would expect R naught, which is the number of infections produced by a single individual, to be based on some probability of transmission, some measure of how long that farm is infectious for, and then how many contacts are made during that period. So we know that it's based on all three of those things. We don't necessarily have to know the probability of transmission or the duration of infection. If we know the contact rate, we can at least say that R naught should be proportional or should be correlated with the contact rate. So we can calculate the overall R naught for each of our systems. So the overall vulnerability of our systems just based on the patterns of contact. And that's what these numbers across the top here show. This is the R naught that we'd expect just based on the contact patterns. We see that the production systems are not all the same. Production system C is doing something differently than the other ones. That's making the network more vulnerable to spread. We also can look at, down here, the individual farm's contribution to R naught. And we do this just by saying, okay, let's remove this farm from the network, recalculate R naught, recalculate the vulnerability, and then saying, okay, how much did it change when we removed that farm? And then we call that the farm's contribution to R naught. So we see that some farms are really important. They're way out here in the distribution. These are, potential super spreaders, very important in maintaining the connectivity of these networks. And then most farms are, relatively low in their individual contribution to R naught. So what we really want to do is say, well, okay, can we use all this information to target preventative measures or surveillance or something to better control disease? So what we did is we actually asked, can we select specific farms, target specific farms in the network for some sort of intervention or some sort of additional control? And essentially what we do then is we just remove them as if they're no longer part of potential infection chains. And we can experiment with them removing farms based on their mean infection potential, based on their degree, just how many contacts they have. What if we just randomly remove farms and see how effective that we can be? So I think in this example that she's highlighting here is that if you can figure out which farm this farm is, the one that X'd out, you can do a lot to protect your system from rapid spread of disease versus if you had targeted this farm where you've really only protected the 2 additional farms. So what you're looking at here is we essentially did this. We started with removing 1 farm, recalculating R naught, then removing 2 farms, recalculating R naught, until we have, an increasing fraction of the population removed. And then we calculate how does R naught change relative to what it was at the beginning, right? So the fractional reduction of R naught relative to the full network. And what we find is that if we target farms based on their mean protection or their mean infection potential, that we can get an 80% reduction in R naught, so an 80% reduction in our vulnerability to spread if we target these farms in order of their mean infection potential. And that's what these 3 lines show here. And then we do much better at targeting them than if we had just randomly removed an equal proportion of farms, where if we had done that, we have to remove about 80% of the farms or target 80% of the farms to get the same 80% reduction in the vulnerability of the network. Of course, this is a kind of a simplified system. One thing we're not considering is that there are different levels of biosecurity at different farms, different production types. We kind of, in this analysis, treat them all equal. So that's one limitation of this sort of work. And we only focused on movement-based transmission, which is, of course, not the only way pathogens can get around. We don't talk about potential airborne spread. We don't talk about feed trucks or personnel or anything else that could be moving pathogens from farm to farm. And we only have 1 year of data, and so we don't have a good feeling about how much, if you measure this in 1 year, if the same farms would be the potential super spreaders in the next year as they were this year. So we would need more data to actually say how predictable is this through time. But one thing I was thinking about that I really learned about from this conference is I always thought about targeting farms in terms of surveillance or vaccination or some other method or of control or intervention. One thing that's really come up as a light bulb for me is maybe if you can identify those farms, maybe we should be thinking about paying particular attention to the trucks going down those farms and targeting those trucks for the extra scrutiny on the truck washes. So that was something I hadn't really considered before. So I appreciate all the interactions here and helping me think about these. Just briefly, I want to recognize Amy's two advisors, which is Andres Perez and Megan Kraft, and then that's me, and then our funding sources for this work. So thank you.